So if you were viewing with us last week, we started talking about magnetism. Again, magnets usually have a north and a south pole. Opposite ends of magnets attract each other, and the same ends of magnets repel each other. Not everything is magnetic. However, magnetism is really created by moving charge. And so if I run, you can see this bolt, which I've wrapped some wire around, is not magnetic. It has no effect at all on this. And of course, aluminum is not magnetic anyway, so it won't pick either one of those up. However, if I give this bolt with a wire around it some current, this is kind of an old Boy Scout trick, still doesn't do anything to the aluminum, but now it sure picks up that little metal plate. And if I just turn the current down, the magnetism goes away and the little metal plate falls to the ground. Now, you can show that electrical current is also affected by magnets. And I can do that. Here is a piece of aluminum foil, and as you can see, the aluminum foil has no reaction to this magnet at all. However, aluminum is a conductor. So what I'm going to do is run some electricity through this aluminum foil. Connect one end to the positive and one end to the negative. And I have an ammeter over here so I can watch the amount of current that I'm running through my aluminum foil. And right now, there's roughly just under 2.8 amps of electrical current. A little while ago, that aluminum foil did nothing, but now you can see it knows right away that there's a magnet around. If I reverse the magnet, the force reverses. If I turn the magnet the other direction, and it's not just that magnet, any magnet that I bring nearby will cause the aluminum foil, because the electrons, which are moving through the aluminum foil, can feel the magnetic field. Now, this has a very practical application for all of us. It's not just a cute physics demonstration. Here is a very small copper coil of wire in the form of a square, and I've got a little bracket here which allows me to put that coil in between those two brackets that hold it, and the coil can spin. Now, the coil won't spin on its own. However, if I connect both ends of my power supply to the brackets are copper, so electricity can go through the coil and back around. So I have there a little coil that has current going through it. I haven't turned it up yet, but I will in a second. So I'll turn my current up here. And now I should have some current going through the coil, and it may need a little push. I'm not sure I'm going the right direction here. There we go. And of course what happens is every time the coil comes around, I should be able to do a little better than that. It gets a push from the magnet, and the coil should keep spinning. See if I can get it just a little better. I may, yeah, there we go. And that absolutely is the basis of an electrical motor. Every time the coil comes around, it feels the magnet, and it gets another push from the magnetic field. Now, that's a very kind of simple, non-useful type of motor, but they do make things that are a lot more useful. So here is a coil. It's a little bit hard to see. It's inside of here, and there are magnets around that coil. And if I connect the power to this coil, like this, I now have it connected, and I'll turn up the electricity, and sure enough, there's your electrical motor. Now that electrical motor could be your mom's blender making something for dinner. It could be running a lawnmower. It could be even your car if it's a powerful enough motor. But that basically is how magnetism and electricity go together to make something that's very useful for our world.